So how do you calculate the gravitational intensity due to a solid sphere? Well, in order to do that, we are going to use the concept of Gauss law of gravitation. The Gauss law of gravitation simply states that if you have an integral I dot dA calculated over the entire surface, then that is just equal to 4 pi g times the mass enclosed. Well, we are going to talk about this integral and about all of its components individually, but first let's consider a solid sphere. So, suppose we have a solid sphere with some radius r, and we are supposed to figure out the gravitational field intensity at some point P at a distance r from the center of the sphere. So let's start by drawing a Gaussian sphere or a imaginary Gaussian surface around this solid sphere. Well, if you pay attention, this Gaussian surface has been drawn in such a way that it starts at the point P where you have to figure out the gravitational field intensity, and it is drawn in such a manner that the radius of this Gaussian surface becomes the distance small r from the center of the solid sphere to the point P. Now let me just write this integral once again. Let me talk about the individual components of this integral. So I is just the gravitational field intensity that we need to figure out. Then what about dA? Well, dA is just the area of the Gaussian surface. Well, one thing to consider is that if we have a sphere and if we consider a small elemental area on its surface, then the area vector coming out of the surface is always perpendicular to the surface itself. And then suppose a lot of flux of gravitational intensity is coming out of the surface, that then at any point you can always find a surface such that the area vector is always parallel to the flux. Therefore, I dot dA can be written as simply the product of I and dA. So what about this integral now? Well, this integral can now just be written as I dA equals minus 4 pi g times mass enclosed. I can pull the I outside of this integral and we'll have the integral of dA equals 4 pi g times mass enclosed. Well, dA is just the elemental area of this Gaussian sphere. Therefore, the integral of dA is just going to give us the total area. This implies we can write that I times 4 pi r square is equal to minus 4 pi g times mass enclosed. This 4 pi gets cancelled and we are left with I times r square equals minus g times mass enclosed. Let me call this equation 1. Now what about the mass enclosed? Well, mass enclosed is just the total mass that has been occupied by this Gaussian sphere. Well, in this case, when we have the point outside the solid sphere, the entire solid sphere has been enclosed by this Gaussian surface. Therefore, this mass enclosed is just going to be the total mass of the sphere. Now, if we substitute this in equation 1, we get I r square equals minus gm. This implies I equals minus gm by small r square. If we try to write this in the vector form, it is going to give us I equals minus gm by r square times the direction vector. Now, what about the situation when you have to calculate the field intensity at some inside point of the solid sphere? Well, in this case also, we will start with the same process. We will try to make a Gaussian surface inside this sphere using the same rules that we established before. Now, if I try to write the integral then I dot dA is going to be minus 4 pi g times mass enclosed. Now this time things have changed a bit. However, this part remains the same. So I can write that I times 4 pi r square equals minus 4 pi g times mass enclosed. This 4 pi gets cancelled and we are again left with I times r square equals minus g times mass enclosed. Let me call this equation 2. What about the mass enclosed in this case? Well, in this case, the mass enclosed is not equal to the mass of the entire sphere. As you can see, only this much portion of the sphere has been enclosed by the Gaussian surface. Therefore, the volume occupied and the mass enclosed both are gonna change. Well, we know for any sphere, the density is just given by mass divided by volume. Therefore, the mass can be written as density times the volume. In our case, the mass enclosed would be written as density of the entire sphere times the volume enclosed by the Gaussian surface. Therefore, we can write the mass enclosed as the mass of the entire sphere divided by its original volume times the volume enclosed, which is just going to give us mass divided by 4 by 3 pi capital R cube times 4 by 3 pi small r cube. Again 4 by 3 pi gets cancelled out and we are basically left with mass enclosed equals the original mass times small r cube divided by capital R cube. Let me call this equation 3. Now if I substitute equation 3 to equation 2, we are going to get I r square equals minus g times m small r cube divided by capital R cube. This r square and cube gets cancelled out and we are left with I equals minus gm small r divided by capital R cube. If we try to write this in the vector form, we're going to get I equals minus gm small r divided by capital R cube times the direction vector. Therefore, by using the Gauss law for gravitation, this is the result that we obtain for gravitational field intensity at an external or an internal point of a solid sphere.